Well, hello. Our topic for the day is the rather specialized one of estimating the maximum possible correlation between two variables and the closely related subtopic of making a correction for the attenuation imposed on these correlations by reliability. That was a mouthful. I hope all becomes clear as we proceed. So let us proceed. Again, this is primarily intended as a how-to guide to the basics, but also will include the underlying concepts and why this might possibly matter. Now, as you may recall, test reliability imposes constraints on test validity. A test cannot have a higher degree of predictive power than it has internal consistency or other forms of reliability. Simply put, the part of the test that is simply random noise is random noise, and it won't contribute to any sort of prediction. Okay. Now, again, there are different ways of putting this. If we want to use logical language, we would say, categorical logic, we would say that reliability is a necessary but not sufficient precondition for validity. If we wanted to put it in more dimensional mathematical sounding terms, we would say that the reliability sets an upper limit or an upper bound on validity. Now, so what this implies is that the maximum correlation that could possibly be obtained between a test and any other variable is constrained or determined by the reliability of the test and of the criterion that we are correlating the test with or attempting to predict by means of the test. That outcome or criterion may be another test, but it also could be something that we would not normally think of as a test. So you have two measures, always in a correlation, at least two measures, one of which happens to be the scores on our test. The other is whatever that outcome might be. I've put a few examples on the slide for you. One might wish to use graduate record examination test scores to predict grades in the first year of graduate school. At least that's the main reason why one would ask students to take the test. One might want to correlate performance on a memory test with evidence of cortical atrophy on an MRI. The theory here being that both are reflecting dementia, but the memory test can be given in a much more low-tech environment. You don't need to invest, thousands of dollars each time you give an MRI. Or we could be saying, could form quality on an ink block test, the Rorschach, be correlated with a psychiatrist's diagnosis of schizophrenia? In each case, you have a test score, form quality, memory, GRE, and some other criterion. Now, the validity of a test is often evaluated, judged based on its ability to do exactly this sort of thing. If inkblot form quality doesn't correlate with psychiatric diagnosis, then we think of it as less valuable. Likewise, if GRE scores fail to correlate with first-year grad school grades, we think of the GRE as less valuable. The trouble is that neither the test nor the criterion enjoys perfect reliability. And the part of either one that's random is just going to, be random again. So the question becomes, how strongly could these two variables be correlated? That is, how strongly could the test and the criterion be correlated? And as you probably expect, if you've seen any more of the videos in this series, there is an equation for that. And it's a very simple one in this case. It's the square root of the product of their reliabilities. So R max, the maximum possible correlation, is equal to the square root of the quantity reliability of the test, R11, times reliability of the outcome, criterion, whatever you want to call it, R sub 22. Because again, the part of the test's measures that is random, that's error. It doesn't correlate with anything because randomness doesn't. So how do we get it? This is, again, it's a fairly simple one as these things go. Let's say we take the example of an aptitude test which has reliability of 0.9, very reliable aptitude test. And first year grades have reliability of 0.75. Not terrible. This could be, the GRE and your first year in grad school, for example. Well, how strongly is it possible for such an aptitude test to correlate with such an outcome? Well, that's the square root of the product, 0.9 times 0.75. Multiply those numbers and we get 0.675, and the square root of that is 0.822. So we would say 0.82. Now, one more, and this one we will walk through, but I'll have you jot down the numbers and see if they make sense to you even before I say any answers. We have a memory test with reliability of 0.84, pretty good clinical memory test. The estimates of cortical atrophy based on the MRI, based on some neurologist or psychiatrist looking at the MRI scan, has reliability of 0.62. So how strongly could those two measures be correlated? So to get that, of course, we would, see, I think you can see my calculator here. I'll say the numbers as we go, just in case. We would take 0.84, reliability of our test, times 0.62, reliability of the doctor's judgment, obtaining 0.5208. And when we take the square root of that, we obtain 0.72, basically. Let's round it down to 0.72. In other words, the highest possible correlation between the memory test and the judgments of the doctors based on MRI would be 0.72. Now, okay, we've done it, but why does it matter? Who cares? There are a couple of reasons why we might care. One is that, as I've already mentioned, we will frequently evaluate the validity of a test based on how strongly related it is, how strongly correlated it is with some other measure, some external criterion. So if we obtain a correlation, of 0.25, we'll say, oh, there's something there, but it's not a whole lot. Now, the trouble here is that we're evaluating the correlations we get against a standard that, 1 is the ceiling, right? 1.00 is the strongest possible correlation. That's how we naturally think once we've, studied our statistics a little bit. But the trouble is that the reliabilities of the measures is actually lowering the ceiling on us. You can't possibly have a correlation in the 90s approaching 1.00 with measures that don't have reliabilities that high. So in addition, often it isn't the test we're studying that's primarily at fault here. It may very well be that the test has high enough reliability. That often is established before you even do a validity study. But the criterion, the important real world outcome, so to speak, that we're trying to get at is itself unreliable. That's a big issue because this isn't the fault of the test you're trying to develop. So you might want to think, instead of thinking of 1.00 as the ceiling, think of the ceiling as that maximum possible correlation. If that happens to be just 0.7 something, then the closer you're getting to 0.7, the better you're doing. We'll circle back to that. There's one other reason I think why this matters, and that is when you're actually running a study. So you're working on a master's thesis, or you're an assistant professor trying to get a bunch of publications out so you'll make tenure somewhere, or in some other stage of your career. You're running studies. Naturally, the measures you're using have limited reliability. That's life. And most of the time, unless you have a lot of funding from somewhere, we're running studies with sort of medium-sized samples. You may have 50 or 100 or so people in your sample, maybe a couple hundred at most. So you may recall in statistics class learning something about power, the power of a study to detect an effect that's really there. We want sufficient power to be able to be pretty sure that if there's something really there, we're going to see it. But if we have very low reliability in one or both of our measures, you're unlikely to get a strong correlation, which means that if you're going to really want the power to find what you think is there, you're either going to need to get a much bigger sample or change to a different set of measures, or possibly give up on that idea altogether and go to plan C. Now, again, that only applies if you're running studies. And to be sure, this is a pretty specialized subject here. But if you are running a study, or developing a test, which is also a kind of study, there's also a process known as correction for attenuation. You see, most of the time, what we're really interested in is how strongly two theoretical variables or constructs are related. If I'm studying achievement motivation, I want to know how much impact, how much of an effect having a high level of achievement motivation would exert on entrepreneurship. If I'm studying psychopathy and I'm studying sensation seeking, I could get interested in just, how strongly related, how closely related are these two things? But in the real world, of course, we can only calculate the relationships between empirical data collected with our imperfect measures. So I could show somebody a series of stories and have them tell pictures to them and have judges rate the achievement imagery in the stories. And now I have a rating of achievement motivation. And I could take, say I did this with a group of students in business school who were all getting their MBAs. I could then track them down in a year or so and see how many of them have started a business. Those are decent ways of trying to capture achievement motivation and entrepreneurship, but they're imperfect. Likewise, I could be studying psychopaths using the Hare psychopathy checklist and sensation seeking using the old Zuckerman sensation seeking scale, but these are not perfect measures of the underlying constructs. So I get whatever correlation I get, and I wonder how strongly related are the theoretical constructs really, knowing that the results I got were attenuated by the less than perfect reliabilities of my measures. There is a way to do this. Now, it's a little bit fishy. I'm going to circle back to that point in a couple of minutes too. So this isn't approved of by everybody, but in general, it is considered to be a legitimate procedure as long as you fess up to what you're doing. So correction for attenuation, and surprise, surprise, there's an equation for it. You simply take the correlation you got, and we'll call that R sub 1, 2, variable 1 and variable 2's correlation, and divide it by the maximum you could possibly have gotten. So you can do this from scratch, R1, 2 over the square root of the product, R1, 1, R2, 2, or if you already know R max, just R over R max, same thing. So getting it, again, not one of your more complicated procedures here. We knew that the aptitude test for law students has reliability of 0.9. We know that first-year law school grades have reliability of 0.75. We find that aptitude test scores, LSAT scores in this case, correlate with first-year grades at 0.4. All these are made-up data, by the way. So the true correlation, well, 0.4 is the numerator. That's, R1, 2. The denominator is the square root of the product of their reliabilities. And these are the same numbers we used before. So you get 0.82. So the answer is, well, the true correlation is more like 0.49. Now, that's not the correlation between law school admissions test and law school grades. That's only 0.4. But whatever it is the law school test is getting at, theoretically, and whatever it is that law professors are getting at when they assign grades to students, those underlying theoretical constructs, in fact, correlate at 0.49. So what we've come to realize is that your aptitude is a little more strongly related to your achievement potential than the original results would have led you to believe. Now, let's look at one of our other examples here. We have the memory test, reliability 0.84, the MRI analyses, reliability 0.62. We find that the memory test scores correlate with MRI results at 0.5, R equals 0.5. Pretty strong correlation, by the way, but with a lot of room between that and 1. So how strongly related are memory and dementia? Now, remember, we have only an imperfect measure of memory and only an imperfect measure of dementia here. So once again, the numerator is simply the correlation we got. That's nice and easy. And the denominator will be the square root of the product of the reliabilities, the maximum possible correlation, which you may recall was 0.72. So again, these are fictitious data. And when I said remember, it's because these are the same numbers we used before. The true correlation between memory and dementia would come out to 0.5 divided by 0.72, right, which would be 0.69. So in this case, what we've found is that the relationship between memory and dementia is quite a bit stronger than those original results would have led us to believe. I mean, 0.69 is a very high correlation. What got in the way wasn't that the memory test was terribly limited. It's that the doctor's interpretation of MRI scans had relatively low reliability. Okay, so wrapping up this little mini presentation, knowing what the maximum possible correlation is helpful when you're trying to design studies that have a fighting chance of actually working, of actually obtaining the results that are really there that you thought would be there, and not ending up with non-significant results, even though your hypothesis was correct. It also can help us to kind of interpret the correlations we actually get, because again, whatever you get has to be understood in terms of or relative to what was possible in the first place. Correcting for attenuation can make this more transparent to a reader. Now, I do want to emphasize again, you've got to specify that you're doing this. You can't simply report this as if you got it as the correlation. You didn't. I would say that you should always report the correlation you obtained and the reliabilities of both measures, as well as the corrected correlation. And that way your reader, your informed reader, can check your numbers and for themselves and will not be misled. So you really have to make this explicit. Otherwise, it would be research malpractice, really. But that's it for today. We will see you next time for another exciting episode in Adventures in Psychometrics. And that said, good day.